on the rightmost digit, what is the operation of addition? It is equal to what's called XOR gate. XOR gate means if the XOR gate takes two input. If both are 0, the output is 0. If one is 1, the other one is 0, the output is 1. Because it's 0 or 1 is equal to 1. But it's exclusive OR, meaning that if both of them are 1, it gives you 0. Right? Well, you can see that adding binary number, just look at the last one, is equivalent to XOR gate. This kind of thing, this kind of insight is exactly how you build classical computer. You turn mathematics on binary number, into logic gates on bit. And then you turn the bit into transistor. You turn XOR into electronic circuit. That's it. So if you can add, you can subtract, and then you can multiply, you can do everything is built up from this. So you have to understand that a bit is either 0 or 1. You manipulate a string of bits, right? Because it has more information than just 0 and 1, using basically complex combination of logic gates. And that's what classical computer is all about, right? That's what classical computer is all about. Now, we are going to go to quantum computer. Again, I'm going to start with 1 qubit and then 2 qubit. And, once you have 2, you can have 10, theoretically, right? Okay, so let's go to a qubit. First of all, a qubit, you guys know what a Schrodinger's cat is, right? No? It's a cat that's inside a box because this is a quantum mechanical device. It's kind of 0 or 1. It's like a spinning coin. If it's 1, poison is released and the cat dies. If it's 0, the poison is not released and the cat is alive. The point is that when you close the box, you don't know if the cat's alive or dead. But once you open it, yeah, it's alive or dead. But anyway, that's the analogy. Anyway, so that's quantum superposition. So in 1 bit, instead of having 0 or 1, you have both. Now, I'll show you a definition later, okay? But so you kind of like both 1 and 0, or kind of spinning coin. And then when you have a whole bunch of qubits together, they can kind of like, unlike classical bits, where each bit here are independently manipulated. Okay? In other words, you can manipulate one without manipulating the other. Okay? With quantum mechanical bits, it's possible if you did certain things to it to some kind of entangle 2 qubits together so that if you get some result for one, the other one has to have the specified result. It can't differ. It's like they have a spiritual connection. Okay, so that's the difference. So the 2 differences is, number 1, the bits alone is not just 0 or 1. It's kind of like spinning. It has probability of 0, it has probability of 1, but when you finish the computation, turn on the light, open the curtain, open your eyes, it has to be either 1 or 0. But if you did this 1,000 times, it will be 1 and 0 in the same probability that you started with. So that's 1 qubit. But when you have 2 qubit, another thing you need to know is that somehow they can be entangled. Now, I'll talk to you about what entangled means. The point is that you can kind of like make them spiritual kin, something like that. Analogy would be something like this. Let's say you have a spiritual kin. You have probability of being happy and sad. On a given day, you could be happy and sad. But if you have a spiritual twin, who lives in Paris. What happened is that because you are a spiritual twin, you have random probability of being happy and sad. But every single day, if you wake up sad, your spiritual twin is also sad. Even though, you haven't called the other person, there's no communication. But you know that your spiritual twin is also sad because you have been entangled spiritually. Yeah, that's analogy of this. Okay, we'll see how that works later. Okay. It's precisely these two effects, quantum superposition and quantum entanglement, that allows for this powerful calculation. So it's that weird, strange thing. Again, superposition is weird, right? A bit is not 1 or 0, but a bit of both. Until you open your eyes and it's something. And 2 bits can be entangled so that you can separate them far apart. One is here, the other one's at the other side of the galaxy. But if this one wake up sad, the other one wake up sad. Okay, without sending a message. Okay, so these are the weird quantum effects that they're going to use. Okay, so now I'm going to go to this slide, which has much nicer. Okay, right. First thing first, instead of 0 or 1, I'm going to put this kind of funny bracket. Can you see it? This bracket, don't worry why it looks that way. Okay, it's called Dirac notation, Dirac physicists. The first bracket is straight. The second bracket looks like a greater sign. Okay, and this represents okay, this here represents state. Okay, so this can be what? 0 or 1. Okay, 0, 1. Now, I told you, some of you, that actually the mathematics of quantum computing is linear algebra. So this is what physicists use. But if you're going to do calculation with matrix algebra, you might as well have a notation for a matrix algebra object, right? And this thing, so this is a wave function. It can either be 0, okay, or 1. Okay, so what's the wave function? The wave function is equal to A 0 plus B 1. This is the wave function. Okay, just remember what this picture looks like. Now, if I see this, it has A2 is equal to the probability of 0. Okay, and B squared is equal to probability of state 1. Just remember this. Okay, just remember this. Again, this is a wave function. So what's the wave function? The wave function is A and B. Okay. Now, this is kind of like, this is what physicists work with, okay? But when I do quantum computing, it's easier to think of this logic gate as matrix multiplication. So if I want to work with matrix multiplication, I have to work with vector, right? So now I have to create a vector representation of a state. So if this is head, this is tail, this is my vector representation. Representation of 0 is a 1, 0. Okay, so this is a qubit, so is this, but this is in linear algebra representation. This is in physics. So physicists would write this. You guys, myself, if I want to work with matrix algebra, if I want to translate this into mathematical code, I would work with this. Okay? So whenever you see 0, you think of tail. Whenever you see 1, you think of head. Well, so we now have 3 representations. Physicists have this funny bracket, 0 or 1. A magician has a head or tail, right? You, as a student of linear algebra, has 2 vectors. It's always this unit vector, 1, 0, and 0, 1. Okay? Now, this is matrix multiplication. You know how to do that, right? This slide just has a review. Now, here's a funny thing. Well, not funny thing, but if you think of a classical bit, again, a classical bit, 1 or 0, right? So I'm just going to have 1 or 0. I'm not mixing them now. But instead of writing 1 or 0, I write 1, 0 and 0, 1, okay? So this is my classical representation of 0. This is my classical representation of 1. So here's the deal. Think of this as one transistor, can be 0 or 1. What can I do with electronic circuit? What can I do electronic circuit? I can set it to 0. This is called constant 0. Meaning, I don't care what the transistor's value is, I'm going to set it to 0. Off. Constant 1 means I don't care if it's 0 or 1, off or on, I'm going to make it 1 or on. That's called set constant. The other one called identity operation, meaning whatever state it is, I leave it alone. The other one is called flipping or negation. If you 1, I'll turn you to 0. If you 0, I'll turn you to 1. Now, this is why this matrix of this electronic operation is done with electronic circuit. In linear algebra, it's done with matrix multiplication. And you can verify for yourself, right? This matrix is identity matrix. It does nothing. It leaves it alone. This thing just flips it. This thing just set it to one value. This thing just set it to the other value no matter what. Right? So you can see it, right? You can see, right? So just as the classical computer turns mathematical operation into logic gate, here I'm talking about this logic gate, except this operation only use one thing, not 2. So it's not okay? Turn it into matrix algebra. Okay. Why would I do that? Here's a fun thing. Well, the point is, well, reversible computing means, now, here's a funny thing, not funny thing. Here's a fun thing. All the operation we talk about will be invertible. Meaning that if you multiply matrix A to X, you get B. You can multiply matrix inverse to B, get back X. That's called invertible. Not only that, the matrix will be its own inverse. So if the matrix A multiplied by X is equal to B, you apply that matrix to B, you get back X. Isn't that cool? It's very kind of nice, very nice to work with. And that's all the quantum operation you will have, will always be this kind. Quantum operation will be invertible, and it will be its own inverse. Now, this case, it's not that interesting because it's working on 1 bit. So I want to work on 2 bit. And this is where you haven't seen this matrix algebra before, because you have done dot product, you haven't done tensor product. This is what a tensor product looks like. Tensor product basically spell out the combination. So if you have, okay, just think of pure matrix operation. 1, 2, and 3, 4. Now this is not a bit, right? A bit is 1, 0, and 0, 1, okay? But a tensor algebra, a tensor product in linear algebra, this you haven't taken. You just basically, for every 1, you take 3 and 4. For every 2, you also take 3 and 4. So you say 1 times 3, 1 times 4, and then 2 times 3, 2 times 4. Does that make sense? And you can do this successively, right? So this one, this times this one, times this one, this one times this one, this one. So I get 4. And I get this one times the 4 of them, this one times the 4. Can you see this? Right. Now, this is how tensor algebra, tensor product works in linear algebra. Now let's apply it to the bit, right? So now what is this number? This is 1, this is 1, this is 0. So when I multiply this, I get this. Okay? Right. Now watch the magic. Okay? Remember I told you that the most powerful thing about quantum computing is it reduces the scaling. For example, 2 to the n is a big number, but n is not a big number. Okay? Watch this. How many numbers do I have here? 1, 2, 3, 4, 5, 6, 7, 8. I have 8 numbers. How many, let's call this bit, okay? How many bit do I have? 1, 2, 3. Right? So if I have 3 bit, I can express 2 to the 3 numbers. Right? That's, yeah. Okay. Well, the point is with classical bit, with classical computing, the bits is always 0, 1, or 1, 0. The bit is always 0, 1, or 1, 0. And if you're going to do any kind of calculation, you have to go through them all. But because of the funny principle of superposition and entanglement, somehow you can spread the information globally. So somehow it doesn't have to explore all 2 to the n. And that's the power of quantum computing. We'll get to it. Okay, we'll get to it. What you have to recognize right now is you can see this here. This is the number of bit. This is the number of number that it expressed. If it's classical bit, you have to go through one of them one by one. If it's quantum bit, somehow you have a global way of looking. Okay, and I'll show you how it works. But we haven't got to quantum bit yet because right now it's still traditional bit, right? 0 and 1, 1, 0. Now I told you that I want something like this, right? Right? So if traditional bit looks like this, okay, right? The quantum bit would also, okay, so the quantum bit is going to look like except it doesn't have to be 1 or 0. It's going to be some number. It's going to be some number such that a squared plus b squared has to be 1 because it has to be probability, right? So a qubit, just like a traditional bit, is either 0, 1. So a traditional bit is 0, 1, or 1, 0. When you have 2 bits together, you get something like that. When you have 3 bits together, you get something like this. So this is traditional 3-bit. Likewise, quantum bit or qubit is going to look like this. Right? And so if I have quantum, let's say this 2, and I have them like this. What's that going to be equal to? A2, A1, A2, B1, B2, A1, B2, B1, right? Except now they don't have to be 0 or 1. It's going to be some number. So now again, just as this thing square plus this thing square is equal to 1, this thing square plus this thing square plus this thing square plus this thing square is also going to be equal to 1, right? So now you are going to, let's put it this way, you're working with vector of square root of probability. Does that make sense? Because you have to square first, okay? So if you square this, you square this, you square this, you square this, you get vector of probability, right? PMF, basically, okay? But we're working with the square root of that, plus or minus. So it's going to look like this, same as this, except now this thing square plus 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 this thing square is equal to 1. But it doesn't have to be 0 and 1 by itself. Now, because the traditional bit, these things, it has to work the same way. So 0 square plus 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 1 square plus 0 square is equal to 1. So there can only be only 1. Okay? Whereas, so everything has to be 0 except one element. But with quantum bit, you can have superposition. That's what it means. Okay, there we go. Okay. Now, I'm going to say this quickly. Just because, remember when you use this addition on the last bit, it's called exclusive OR. So you can think of logical gates that build a complexity. In fact, in reality, in computing, I think it's the NAND gate that's the most fundamental. Okay, it's the logic gate that builds the basic circuitry. Likewise, in quantum computing, they also have fundamental logic gate, and that's called control NOT. A control NOT just simply say, you look at the first bit. If it's 0, you leave the second one alone. If the first bit is 1, you flip the second one. Don't ask me why this makes sense, but this is a kind of logic gate that's going to be applied to quantum bit. And this can build up all the complexity of a quantum computing. There's some other operation, but this is a big guy. This is a main guy. Okay, it's called C0, C for control. Okay, so it looks at the first bit. If the first bit is 0, leave the second one alone. If the first bit is 1, you flip the second. That's what it means. Okay, so in the physics notation, it looks like this. Now you can obviously apply this to see, you can apply to this. So that's why just as a logic gate here is equal to matrix multiplication. When you have 2 qubits together, see, 1 qubit, another qubit, right? You put them together, you get this combined state. The operation of that is called C0. And that is equivalent to this funny matrix. Basically, identity matrix here and a flip matrix here. And you can prove, I'll give you the slides. Okay, this is from that guy, by the way, right? So you can see that, you look at the first one. If it's 1, then you flip the second one. First one, flip the second one. Right? Now, if the first one is 0, leave it alone. First one is 0, leave it alone. Okay. That's why I can actually develop a whole course of quantum computing. Instead of formulating as a physics object, I can formulate it as linear algebra. And then you can learn about all the operation it can perform. Okay. So that's it. That's it. Now, so let's look at some real number. This is one of those qubit, guys. See? Again, look at how cool this is. The qubit is like a wave function, or it is a wave function. That's why just like a wave function, it can be negative. But if you square it, you get probability. Same here, look. If you square this, you get 1/2. Square this, you get 1/2. So it's 1/2, 1/2. If you square this, you get 1/4. If you square this, you get 3/4. 3/4 plus 1/4 is equal to 1. Same here, right? So it could be, so these are all legit qubit, right? Just as quantum mechanics work with the wave function, quantum computing doesn't put differential equation on this. It operates matrix multiplication on this. Okay, remember? Billiard ball, differential equation, classical physics. Wave function, partial differential equation, in particular Schrodinger's equation, quantum mechanics. In this case, the wave function is actually the value of the qubits together. In this case, just 1 qubit. In this case, 2. And instead of having some kind of dynamic based on, I don't know, maybe gravity, not quite gravity, obviously, okay? Instead of applying Schrodinger's equation, you apply matrix multiplication because you are manipulating, right? Again, computing is not the same thing as mechanics. Mechanics is studying a real system, build hit each other, electron bounce off each other or whatever, right? We're not studying that. We are manipulating the wave function. So how do we manipulate? Multiply with matrix. Okay? So just as the C naught is a fundamental, okay, there are actually 4 that you need to know if you were going to work in this, but today you don't need to know many. You need to know this guy. You need to know another gate. This gate is like the mother of all gates. It's called Hadamard gate. What it does is that it turns classical into quantum and back. Meaning, it turns something that's either definitely 0 or 1 into superposition. But again, if you multiply it twice, apply on the same thing, you get it back. Now you can verify this, okay? So this is definitely like a classical bit, right? 1, 0. You multiply by this gate and you get a mixture. You multiply again, you get back this. You can do this for your homework. Okay? Same here. So what does it do? It's saying that if I have a classical bit, I can mush it up into a quantum bit. Okay? And if I have a mushy quantum bit, I can multiply this and get some value. Okay. So that's what Hadamard gate does. See? I start with a mushy, I end up with definite. I start with definite, I end up with mushy. I start with mushy, I end up with definite. Now, this is the most important picture I want you guys to see. This is actually how quantum computing is performed. Basically, you guys look at this. I have 2 states, right? 2 states. What is 0, 1? 0, 1. That's value 1, right? Now, I want to put this on a clock. And think of the first one as an x coordinate and the second one as a y coordinate. So if I start with a value 0, what's value 0? State 0. Flip off. That is 1 and 0, right? So it's 1x, 0y. This is this. Okay? Now, this could be classical bit because it's very definite, right? Another one that's also could be classical bit is this guy. 0 and 1, right? Because this represents number 1, it's written as 0 and 1. So 0x, 1y. So classical bit is basically these 2 guys. The quantum bit, the superposition, is any value on this circle. Because when you take the square of it, is equal to 1. All of this, any point, take any point on this. Take the first value square, add the second value square, what do you get? 1. This is a unit circle. So the superposition in classical or in quantum bit is basically say, hey, from 2 points, 2 value, you have infinitely many value on a unit circle. Now, I don't want to discourage you, but professional quantum computer scientists, they work with imaginary number. So they have another plane going. So it's a sphere. It's not a unit circle. It's called box sphere. Okay, but don't worry. This is good enough. The point is this. You guys remember that Hadamard? You guys remember that that gate? Yeah. Yeah. So this gate here, all this gate here, just basically move points around unit circle. In particular, Hadamard gate, I start with something definite. Sorry. I start with something definite. I start with something definite. I get something mushy. What do you think happened? This matrix is basically moving the needles from where? From here to here. Okay. Yeah. So what's this one do? Okay, this one is a flip bit, right? So this one does this one does Hadamard. Okay, so from definite to mushy, from mushy to definite, from definite to mushy, from mushy to definite. Except this mushy is not classical because it's -1, right? So again, classical bit is only 2 value, this or that, this or that, this or that, this or that. Qubit is any value in between. Again, if my quantum machine has this value as a solution, okay, what happened? This kind of like indecisive, right? Half the time it's going to collapse to this. Half the time it's going to collapse to that. What I mean by collapse is turn on the light, stop the computation. Okay, it's called quantum collapse. The technical word for it is collapse. So this is a classical bit. This is a quantum bit. But at the end of the calculation, you have to get some number, right? So it collapsed to classical bit. Okay, it collapsed. Now, if my solution is this, what am I going to get from my histogram? Half the time it's going to be 1, half the time it's going to be 0, right? So what happened is your job as a programmer is to make sure that the probability is maximized for the solution. There's no calculation here. There's only like 1 bit, so there's no calculation. But you can imagine that there's like a zillion calculation and the result is some number, okay? So the best solution is 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. Well, what you want to do is maximize the probability of that. Okay, and when you send it to a quantum computer 1,000 times, it's going to have a very high histogram. Okay. Now, this, by the way, is called quantum programming. It looks a little bit funny, right? Because you're used to Python or mathematical program, x is equal to 5, y is equal to x squared. But those are based on operating the NAND gate, the XOR gate, right? That's built up. Well, think of that. Think of computer scientists working on digital computer in 1950s. You have to work with gates as well. It's the same here. So yes, there will be a higher level on top of this, but I want to show you that this is fundamentally what the gate is all about. Okay, so before you get to higher level, there's like a manipulation of bits. programming. And this is what quantum programming is about. Now, higher level of this is expressed with a Python interface called Qiskit. Anybody heard of that? Basically, Qiskit is for guys with Python laptop to key in something like this, symbolically. Instead of doing this kind of like, put the gates down, I think in this presentation, the guy shows you an example of Qiskit. Anyway. Now, the rest of it is too difficult. It's more complicated, but I can show you something which I made up actually this morning for you guys. And I'll give you guys this. This is one of the most powerful things. I mean, this is scary powerful. Okay. Again, one of you has COVID. There are 20 of you. Best case is the first guy. Worst case is the 20th guy. So basically, as the number of you guys n gets bigger, it takes that many steps on the order of. But what if I can devise a scheme to test for COVID where I can pretty much tell who has the COVID by performing this experiment square root of n time? That's pretty cool. Now, if there are 4 of you, okay, square root of 4 is 2. 2 versus 4 is not a big deal. But if there's 100 of you, instead of, if there are 256 of you, instead of doing 256, I only need to do 16. Yeah, that's pretty cool. Yeah, something like that, right? So if there are 1 million of you, right, how many tests do I need to perform? About 1,000, not 1 million. Okay, let's go to it. I just wrote this for you this morning. Now, remember, I'm going to use 2 words, state. Yeah. Well, let's okay, this algorithm you can read in detail here. It's called Grover's algorithm. The guy who invented it is a genius. Well, all of these people. Shor's algorithm, invented by Shor, who's also a genius. All these people are brilliant. Okay, here's the deal. Here's the deal. Okay. I ask a question. Say 20 of you right now. 20 of you right now. You have COVID. You have COVID. You don't tell me. You don't tell me. But because I can do certain kind of tests, okay? First thing first, I'm going to give everybody same probability of being the COVID guy. So same probability mean 1 over 20, 1 over 20, 1 over 20, 1 over 20, right? But I'm not working with probability. I'm working with state. So what am I going to do? I'm going to give you 1 over square root 20. All of you have this number. Okay? All of you has this number. Okay? I'm not going to test you one by one. What I'm going to do is this. I'm going to say, whoever has COVID, you know who you are. Flip that number. Flip that number. Okay? So now, secretly, you don't tell me, right? You have COVID. You flip the number from 1 over square root 20 to minus 1 over 20. Okay? That's called an oracle function. So the state is a vector of values, each of which square add up to 1. If the target, that's you, what I'm going to do is I create a copy of the state internally called S. Okay? Okay, so right now, S is a vector of 1 over square root 20 of them. And then the target is, let's say 1, 2, 3. Okay, U number 3. Okay, you don't tell me, okay, let's make it U number 13, unlucky number, okay? So S13 becomes minus 1 over square root 20, okay? Imagine that, right? So now, secretly, think of a bar chart. Everybody has 1 over square root 20. If you square this, you get PMF, right? Okay. Work with this. The 13 guy flip upside down. I flip you upside down. Okay. You flip yourself. You don't tell me. Okay. Now, here's where entanglement comes in. I'm not applying individual tests, but somehow, because you guys are not independent, I can put you in a sort of like a cloud knowledge base, so that I don't know who you are, but I can calculate the group average. The group average is 1 over square root 20, 19 times minus 1 over square root 20. So actually, the average would be 18 divided by square root 20 divided by 20. Okay? Now, just imagine this in your head. I'll show you numerically, so it's okay. But I'll try to get you to visualize this in your head. So now, you used to have 1 over 20, square root 20, you flip. I calculate an average of you guys. And I ask all of you to do this kind of like gymnastic. So if you are 2 above the average, you go 2 down. You kind of pivot. This is called inversion around the average. Okay. What happened? What do you think happened? The average used to be 1 over square root 20th, right? Because everybody has the same value. But when you flip, you make the average go down, right? So the average is going to be slightly below. When you flip around the average, what happened to all 19 of your friends? They get lower. What happened to you? You get flipped all the way up. Right? So now the new wave function has you sticking out. Pretty cool. If I did this mathematically, square root of n times, your probability sticking out will be 1. Everybody will die away. Well, not like exactly 1, but close to 1. Let me say this again. One of you has COVID. I can test one of you. Or I can say, hey, you all have equal probability. You know who you are, who has COVID, flip yourself upside down. Take the class average, flip around the average, inversion around the average. You're going to keep sticking up. I do this square root of n times. Now, the detail is mathematical, so I'm obviously, okay? You will stick up. Let's see how it works. So this is you flipping. It's called oracle. The reason it's called oracle is from the Greek. Oracle means, like the god. It's a hidden answer of nature. Okay. Inversion about the mean, just basically take a state, flip it around me, and the way you do it is minus state plus twice of the mean as the state. And then try that, but it works, come back like that. Okay. So one step of Grover iteration is basically these 2 steps together. Right? And the probability, you just take the square of it. Yeah? Well, I don't have to have n actually. Better not n. Well, I can have n. Yeah, that's it. Well, no n better. N means numerical. Now, how do I apply this function this many times? I use mathematical construct called fold. What it does when I apply this, this is just a shorthand. This is one of those things where it's very difficult if you were to do it with list iteration in Python. Or In mathematics, you can also do for loop, but it's very clumsy. This is actually very elegant. What it means is that apply f to x with additional argument a, and a. Now I can change this, so it's very flexible. But in this case, if I do this, what it means is that I apply this 3 times. Okay. So what I'm going to do, I'm going to apply this function 3 times on the state with the target. So this is where this whole thing comes in. Okay. Now I do various bit. Let me show you this one. This is more interesting. Okay. You guys see this? It's a bit hard to see. Let's say there are 9 of you. The reason I made example square so that I can take the number step as a square root minimum. Anyway, so there are 9 of you. There are 9 of you. Okay. What I did was I applied this iteration step once, twice. Actually, I could do it 3 times, but right now you can see now this is the probability. Okay. Well, it's not probability, it's a state, right? If I square this, 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 and add them, it's all going to be equal to 1. But you can see that right away, this one is bigger, right? This is almost 1. Now, if n is bigger, I probably need more step. Okay. Right? So now you can see that this here, I randomize integer. I don't know what number it is. It turns out to be this second guy, I think. Yeah. Okay. So this is a state because I squared it. I squared it. So let's instead of iterate over step, let's do this. Yeah. Let's do this table of yeah. Well, I don't want to mess it up now, but I can do n here. And that's okay. But you get the point, right? So, oh yeah, I know what I should do. I should do this. Instead of doing a table, I should do bar chart. Yeah, let's do that. Let's do bar chart. Bar chart. Does that work? Yeah, that is. Okay. See? The first time, this is a state, right? I flip you. This is the second one. So you can see why, every time so this happened to be 16 and the target state is the 15 one. So every time I make you stick out a little bit more, plus or minus. Now this is a state, so the probability has to be square, right? If you square all this up, you get, so by the time I make 3 iteration, which is square root of 16 is 4, right? So by the time you get to 4th iteration, this guy sticks out. Okay, this is Grover's algorithm. So you can think of this as performing the most efficient binary search in the history of mankind. You guys have ever seen that binary? There's this very fun video actually. You should go to do this. It's kind of very entertaining. Go to YouTube. And well, binary sort is kind of like making things in an order. It's not exactly finding things, but animate binary sort. Yeah, it's this one. It's very interesting. But anyway, all this algorithm, okay, if this is all classical algorithm, if you can have a quantum version of this, it's going to be operating on an entirely different level. Okay. Now this is a sorting algorithm. This is not a search. The other one was a search. Search for the guy with the COVID, right? Finding the key is called finding the target. So instead of n, you get square root of n. Instead of n square, you get maybe n log n. This is, yeah.
So you need to know who can do it before.
I don't know.
Then how does it work?
You know, because you're in the data set. So think of it. When computer represent everything in binary, the data is in binary. The computation is in binary, right? So think of it this way. You know who you are, who has COVID, you are in the binary representation of the data. The point is that the second set of binary is going to take square root of n to dig you out. So it's not, this thing that you know who you are because it's in the data, right? So think of, instead of 20 students, one has COVID, say 20 students, one is named Josephine, and there's only one Josephine. I'm trying to find Josephine. Josephine is in the data set. Is the first one Josephine? Is the second one Josephine? Is the third one Josephine? No, right? Now, instead of doing that, I have 256 students. One of them is Josephine. I represent 256 students as 5, 6, 7 qubit. 7 qubit represent 256, right? So the data that has Josephine or has COVID, has one person has COVID out of 256, right? Basically, 8 qubit. 8 qubit or 256. An ordinary search would require me on the order of 256. Okay, maybe by 128, I have 50-50 chance of uncovering Josephine or COVID. But now I represent this data set in qubit form, and I apply quantum operation on it, which again would require quantum computer that perform this funny gate that you saw. And this takes 16 steps instead of 256. Right? So it's not like the truth isn't out there. The truth is in the data. This says it's just searching, right? Okay.
So you just do the operation to the whole data set.
Exactly. Right, exactly. So if I have a if IBM has 8 qubit machine for me to play, I can hide you in that data set. Okay, Josephine or the one that has COVID in that 8 bit, right? And then do this. And after 8 steps, I should get high probability of this. Okay. Now in reality, they probably wouldn't run it once, maybe run it 1,000 times, get this histogram or something. Okay. But the point is, you can see that this thing that I showed you earlier in Mathematica here, right? If I square this, it's a probability, right? So even the first one, there's a high probability I'll get you. If I run this 1,000 times, I'm pretty sure I'll get you. Okay, you can't hide. So even though it's probabilistic, if you've done this programming right, yeah, you're pretty sure. So now I reduce a step from 256 to 16. Okay, that's pretty cool. That's pretty cool. And again, 256 is not a lot, but you can imagine that there are some problems where the 256 is a number so big, you can't get traditional computer to do it, but 16, you can get quantum computer to do it. The limitation is that I have to get 8 qubit to go together. Does that make sense? Right? So the point is this. The point is you always need, okay, let's say this way. You always need 8 bit. But if that 8 bit is regular bit, you have to search one by one. But if that bit is quantum, I can do something like this, which by magic uncover the hidden target in 16 steps rather than 256 steps. Now, it's hard to imagine what application in your life this is going to play, right? Because most of the time you're not dealing with things that are impossible to solve with traditional computer. But cryptography is one of them, right? So is protein folding, by the way. Except protein folding now is doing with generative AI. They do pretty good. Okay, and that's also huge. So it's hard to give you this intuition beyond what I've given you, but that's basically this is the best I can do, guys. Okay. Now there are other algorithms. Now so notice with traditional computer you have this logic gate. You build this up into general language, right? Like Python, Mathematica, and then you write the algorithm in those languages. With quantum computing, you notice here, all this thing, this function here, this oracle function, this thing here is actually manipulating at the qubit level, kind of, right? So the algorithm is expressed as logic gates. So it's not a general purpose yet. That's why I say quantum computing is not traditional computing very fast. It can't do everything, right? Because it's the general language in computing, you can do all kind of stuff, compress JPEG, God knows what, all kind of things. Okay, but quantum computer is not that generalized yet. And the Qiskit that I mentioned in Python, that's just an interface so that you don't have to do this kind of thing by hand. Okay, because basically this is what quantum programming looks like. Okay, now instead of doing this, this is a bit clumsy, right? It's kind of like, okay, so what you want to do is you write like a Python top level command, could be any language, might as well be Python, to say, okay, I put Hadamard gate here, I put Hadamard gate here, I open the box, a measurement here. Okay, so you see this Hadamard, this is kind of like putting things together. And that Hadamard is very important for mixing everybody. Okay, so that first thing where I say everybody has same equal probability, even though you have COVID, nobody else has, I give everybody same probability. That's the mixing bit. Okay, but it's the mixing bit that has a way of flipping the one who's guilty, so to speak. Right? So that thing you flip, you don't tell me. But I do this 16 times, you stick up.
So it's like quantum computing is like instead of creating an algorithm to like finding the answer, it's like creating an algorithm to like to apply to all of the data and let the one that you're finding appears.
Yes, let the answer have a high probability of showing up. Okay, so like I said earlier, right? Traditional computing is saying, what's f of x? 7.5. Quantum computing would be something like, do this so that the probability of seeing 7.5 on the display is higher than any other number. Which is not nice, like I said, it's not exact, but again, some problem you just can't find a solution. So if you have a way of doing this, you can say, I have a 99% sure, that what are the alternatives? There's 7.5, there's 6.2, there's 8.9, there's all kinds of number. And I plot them on a histogram after I run the quantum computer 1,000 times. And there's a peak. And that peak lands on the number 7.5. That's my answer. Okay? This is how it prints out solution, so to speak. Okay?
And why does it need to be qubit?
Why does it need to be qubit? Because Remember that looking for COVID? This guy is sitting in the back row. He has COVID. Nobody knows he has COVID. So I can search the first 10 guy. If I haven't got COVID, this next guy is not going to tell me. There's no entanglement. It's the entanglement that show your information to the crowd. Because when you flip, how do you show your information? By taking the average. It's like I give everybody this number, 1 over square root 20. Okay? And then you have this kind of like confidential voting. Okay? You send me your number after you flip. You send in, you the only one, nobody else. Send 1 over square root 20 with a minus sign in front of it. Okay? And there's a machine that takes the average. The reason that machine can take an average knowing you have minus 1 over square root 20 is because at once that information is global. And that global information is by tying all the bits together. And that tying bit together is the quantum entanglement. It's a physical property. So think of it this way. If I have a 20 transistor, there's no way I can flip you to 0 and any other transistor would know about it. Right? You cannot transmit your information. Okay, there are 20 transistors. Everybody's all 0. You just 1. You're the only one with the 1. Nobody else can know. But if you are a qubit, a tiny quantum bit made of laser or whatever, plasma, okay, they're working on it. Somehow you can't keep a secret to yourself. I can entangle you. You won't tell anybody. But when you submit your value minus 1 over square root 20, the average goes down. And when I say everybody flip around this average, you stick out. Right? And this is only possible because at the quantum level, you cannot keep your secret. Everybody, this is called entanglement. This is why you need quantum entanglement. So instead of having a local search, do you have COVID? Do you have COVID? Do you have COVID? Do you have COVID? I have a global parallel. It's like even better than parallelism, right? Parallelism means like instead of searching one at a time, I have 2 persons, right? So instead of a room of 256, I separate to 2 rooms of 128. Okay, I have more parallelism. I have 4 guys, okay, into 4 rooms of 64 each. Well, this is global parallelism. This is beyond parallelism. This is global. Immediately you stick out and you keep sticking out with higher and higher and higher probability. By the time I apply this circuitry, square root of n time, you stick out, everybody's quiet. This is why quantum will be, and it's a magic. It's almost like a magic. It's because you can do this. Because at the very qubit level, you can't keep your secret. Okay? You see what I mean?
So the entanglement means you can take the average of every qubit.
This is one form that takes advantage of entanglement. There's other algorithm that does this. This algorithm works by flipping and then other algorithm works some other way. Okay, but the point is it uses basically this thing, this C0, this Hadamard gate. There are about 3 or 4 gates. That's how cool this is. This is how this guy with just 4 basic like W and Z operation, no more than 5, let's say, I think. That are the key one. So when you look at Shor's algorithm, these are the algorithm that cracks RSA code, guys. RSA code would take 5 times the age of universe to crack, right? That can be done in a few hours if you have, let's say, 50 qubit machine. Now, here's where, if you believe in this magic, let's say you believe in this magic, I can tell you why the magic isn't here. The magic isn't here because, remember that thing I told you about, it has to do this kind of like head, tail, spinning, until I open it, right? Imagine how delicate that darn thing is. It's like just a tiny coin, yeah? So that if I just breathe on it, it stops. Think of it that way. It's such a tiny coin, right? A big coin, if I hit the desk, it's still spinning. But if it's a tiny coin, I do this, collapse, head or tail. It stops computation the minute I breathe on it. Imagine if one is sensitive. I have 50 qubits on the desk. How am I going to be so still that none of them gets bothered? It's very hard to keep one qubit from falling on its head. So sensitive. It's so tiny coin. Now I've got 50 coins working together, and they all have to sort of like be so isolated and to keep spinning happily, no noise. That's why quantum computer engineering is all about refrigeration. It has to be cold enough, no vibration. You know, heat is vibration, okay? Right? Atomic vibration, okay? So no heat means no disturbance. So that's why you saw this big picture. I show you this big picture of anyway, the big machine. You can look up the picture of quantum machine. It's big. You know, actually, the quantum bit it's only in here. Everything else is refrigeration. It's refrigeration, and it's so hard that basically the reason we don't crack RSA right now is because we don't have the technology to keep the table still, undisturbed for 50 qubits to tickle undisturbed until it's happy. Okay, that's the technology bit. Now, where are we? Well, let me tell you this, and I believe this honestly, bottom of my heart. We cannot get to the hardware game. It's going to be like generative AI, where there are like 5 players in the world who can do it, really on that scale. Okay, so maybe 1 or 2 different companies in China. IBM certainly has got a head start, right? Google, maybe something with Tesla, I don't know. Okay, but definitely Google, Microsoft. I'm not even sure Microsoft. No, definitely IBM. So all these guys are working on the hardware stuff. There's no reason why somebody in Thailand who doesn't have capital to invest in this big refrigerator cannot come up with algorithm. Right? This is pure intellectual property, guys. Think about it. You can actually devise application waiting for the machine. Now, people have done this for a really hard problem. Maybe you can do it for a problem that's not so hard, but also difficult, you know, like searching for logistic or whatever. So quantum computing is doable. Not the hardware side, because you don't have the capital, but the software side is completely doable without capital, that kind of capital, but you know, using a lot of linear algebra. I truly believe that. There's no reason why, you know, some major breakthrough cannot come from a university in Thailand that doesn't have a supercomputer, never mind quantum computer. Because all this is proven in mathematics, right? And if you can say, if there's an algorithm that's stable and doable, you know, you can say, oh, it only takes 20 qubits for me to crack this thing. And right now, technology is getting so close to 20 qubits, right? But there's a lot of things. There's a lot of things beside that. And then, you know, I haven't talked about things like quantum cryptography and all that, but one other thing you can do is, well, we'll talk about cryptography next week, perhaps. But security doesn't always mean protecting the secret. It sometimes means that it protects the secret or it tells if the secret has been compromised. So quantum anti-cryptography would be something like that. It would be kind of like giving it a signature so that if somebody takes a look at it, you collapse some quantum state and then the whole thing gets scrambled or something like that. No, like when they make the security for the bank cash, right? I don't know if you've seen like Hollywood movies. If you steal like large bag of cash from a bank, right? They're not going to try to save that bag, that bag of cash. You know what they do? They inject the ink so that it destroys everything. It's that thing, right? So the thief can get a hold of it, can't use it because when it opens the bag, this purple ink splash, sort of like radio sensitive ink splash to all the cash, and you can't use that cash anymore. It becomes worthless. So quantum, cryptography is a little bit like that. It's sort of like guarantee that if a secret gets compromised, boom, everything falls apart and that sort of thing. Okay, so we'll talk about cryptography perhaps next week. I'm kind of like thinking, I don't know if next week should be a cryptography / Bitcoin, or sort of like go over the sort of student individual project and prep you guys for the midterm. We'll see. Okay, but I mean, guys, this is probably as abstractly weird or difficult class as you're gonna get. Okay, but I can tell you, I promise you that from the bottom of my heart, the mathematics is completely doable. Just linear algebra. Well, not just, but okay. So if you really want to get to this quantum computing technology, not beyond you guys. So tell me, I don't know if it's worth it. You think Basai would, I'd like to be on the cutting edge. That's why I don't teach math course. That's the only math course I teach is like the pre-course coming in because I want to meet all the students. But I like to be on the teaching on the cutting edge. So I don't know how many Basai students would be in for a full course in quantum computing, because that would take some effort for me to write the text and whatnot. Anyway, so I'm gonna send you, I guess, everything I've got, the slides, the slide from this guy from maybe the link, but you can search for yourself. It's called Quantum Computing for Computer Scientists, except it's like an hour and a half, and you only need like the first 40 minutes. After that's a little bit difficult. Okay, not impossible, just a little bit more involved. Just a lot more gates and talk about teleportation. There is such thing as teleportation, by the way, guys. Yeah, this is called teleportation. I'll just tell you a bit quickly. I can't finish without telling you a bit. Teleportation is like this. Nothing travels faster than the speed of light. When we say nothing, that means you can't send things faster than the speed of light. In particular, you can't send information. However, this entanglement that I told you about, this thing can be separated so far. And if I know that this is, if you're happy, your digital twin is happy, right? That thing can happen simultaneously. Meaning that you wake up, you realize you're happy, your digital twin is so far away, even at the speed of light, you can't tell them. And yet you know that at that exact moment, your digital twin is happy. It's called coordination. It's not transmission. You're not sending anything. So it looks like it's faster than the speed of light, but it's not. Okay. Now, some of you may think, well, maybe because you knew ahead of time you'd be happy or sad. No, it's truly random. And yet, for some reason, you have this universal connection, universal spiritual kindred spirit, that you wake up happy, your digital twin at the other side of the galaxy wakes up happy. Well, you can do this to not send message, but you can send qubit. In other words, you can have two qubits entangle, like with Hadamard gate. Hadamard gate, by fusing 1001, it's like fusing the state together. and then take one, put it on a rocket, go to the other side of the moon, and you know that whatever experiment you perform here, you know the result over there. You can do this. In fact, I did this with, I think, apparently from this talk, I haven't looked up the exact experiment. From this talk, which was, I think, 2018, he mentioned 2013 experiment where Chinese scientists did this with satellites. So with teleportation and entanglement experiment. So this has been proven, guys. This is real science. This is real science. I'll try to find the experimental, but this was 2013. Think about it, guys. Yeah. Again, the technology is, in practical term, we don't have the refrigerator that's stable enough to stabilize 100 qubits staying together. That's all. But it's technological. Okay. So we'll see. Final word. It is possible, hopefully not true, that there is an impossibility hurdle. In other words, no matter how advanced refrigeration technology is, there's an inherent, quote unquote, I'm just going to use a fluffy word, quantum noise, that scales up so fast that you will never, ever get to 50 qubit machine. Possible. Okay, hopefully not. Hopefully that the debate is out. Okay, but that's, you know, that's not for you to worry about. Yeah, but it's a very cool area, and I can't tell you how exciting this subject is, and it's as cool as it gets, guys. I promise you. Okay, so I'll see you next week.